In this video, we have this question. Okay, we have to find the general solution of y prime prime minus 2y prime plus y equal to minus 3 minus x plus x squared. And then, in the fourth part of the question, we are to solve the IVP of the differential equation in question 3 on the condition that we have this IVP, y of 0 equal to minus 2 and y prime of 0 equal to what? 1. I'm going to solve this problem as fast can be. First of all, we need to recognize that the differential equation given to us is y prime prime minus 2y prime plus y equal to minus 3 minus x plus x squared. Clearly, our f of x is this function, alright? And you can see that it is a polynomial. So you should not be thinking the yp value or the yp general form. Is that okay? So we know generally that the general solution is y is equal to yc plus yp. Now let us get our yc. To obtain our yc, we are going to solve but y prime prime, okay, minus 2y prime plus y should be equal to 0, so that we can get our complementary function. And from here, the auxiliary equation is what? M squared minus 2m plus 1 equal to 0. If you factorize this auxiliary equation, you would see clearly that the factors will be minus 1, and so the root of the equation will be plus 1. Therefore, it means that our yc, y subscript c, is equal to, remember that when the roots of the quadratic equation produce real and equal roots, the solution is y equal to a plus bx, or you can say ax plus b in bracket and exponential mx. Is that not so? Our m here, m1 is the same as m2, which is 1. Therefore, the solution would be, alright, this time around, I don't want to use a and b as constant of integration again. I want to use c1 and c2. So this is going to be c1 x plus c2, all in bracket exponential mx. And n here is 1. So 1 times x will give us what? X exponential x. So this is our complementary function. Is that okay? Now we're going to proceed and then solve for yp. But before then, take note that instead of c1x plus c2, it could be c1 plus c2x. Is that okay? There is no rule that it is c1 that must bear this x or it is c2 that must bear the x. No rule like that. Okay, then let us move on. For yp, for the particular integral, we need to recall that for a polynomial function, the yp is now going to be equal to, okay, let's look at it, f of x there. F of x is equal to minus 3 minus x plus x squared. Good. So our yp is now going to take what form? The highest degree in the polynomial is power 2. So it's going to be, let us use a, b, and d as a constant here. It's going to be ax raised to power 2 plus bx, the power will now be reducing until it becomes power 0, plus d. You notice that I jumped c because I've used c as a constant in the first part here, alright? I've used c as a constant in the first part. Now what do we do with this particular integral, that is a yp, for this particular function f of x? We are going to differentiate it 2 times and then substitute into this equation. Let us take this as equation 1, alright? So we differentiate y prime of p. Y prime of p will give us, let's see, we're going to differentiate this term. So that is going to be 2ax plus b. So we'll take this as equation 2. Then to obtain our y prime prime of p is going to be, we'll differentiate the first derivative there. And of course that's going to be 2a. This is equation 3. We shall substitute this equation 1, 2, 3 into the given differential equation and then compare 2 sides. The 2 sides, that's the left and the right. What we are trying to do here is to write the left-hand side as a polynomial as well too, right? So we can be able to compare. The right-hand side is a polynomial, so we'll try to write the left-hand side in such a way that the equation will balance. That's just the whole idea. Once again, don't forget the definition of the solution to a differential equation. It is one that you can differentiate as many times as the order of the differential equation, and then when you substitute it into a differential equation, you should get an identity. So let us do the substitution and see. It implies that, now imagine you're in the example, you want to do this substitution. Do you think it's really ideal for you now to come here, fix into a for y prime prime, and then minus 2 open bracket, you fix in for y prime, and then it's going to take your time. At this point, you need to apply the network of your brain straight ahead. How do we do that? Now watch. Y prime prime has the value of 2a. It's a simple term, so we can substitute it directly. 2a. Then this part is minus 2 times y prime. This is the value of y prime. So straight ahead, use minus 2 to multiply these values here. Are we ready? So let's do that. Minus 2 times 2ax will give us minus 4ax. So minus 4ax. And then we'll move on again. Minus 2 times b will give us minus 2b. Minus 2b. Good. We are now left with plus y. Take note that this is 1y, alright? So our y is this yp here, which is ax squared plus bx plus d. So I'll fix it ax squared plus bx plus d. And that is expected to be equal to the right hand side minus 3 minus x plus x squared. At this point, we're going to compare both sides of the equation. We're going to compare. And the secret of comparing is so that you don't get into a case where you form equation 1, 2, 3 again to solve a form of simultaneous equation if need be. In order to avoid that, you start comparing from the highest degree of the polynomial. The highest degree here is power 2. So in comparing, I will start for x squared. On the left hand side, the quotient of x squared is what? A. You notice that a is equal to, on the right hand side, the quotient of x squared is 1. So clearly the value of a is 1. We are done with this. We move on for the coefficient of x. For the quotient of x. On the left hand side, the quotient of x are what? Let's see. Minus 4a is one of them. Then plus b is the other one. So it becomes minus 4a plus b. Minus 4a plus b equal to, go to the right hand side, the quotient of x there is minus 1. So it becomes minus 1. Notice that a is what? 1. So minus 4 times 1 will give us minus 4. If the minus 4 goes there, it becomes plus 4. Minus 1 plus 4 will give us 3. So the value of b is what? 3. And then we conclude with the constant, okay? Comparing the constant term, right? The constant from the left hand side, let's say the constant, that is the terms without x. The terms without x. 2a is one of them, so I'll pick it, 2a from the left. Another one is minus 2b, look at it. And then the last one is plus d. That's going to be made equal to the constant on the right hand side, which is minus 3. Once again, notice that our a is 1, so 2 times 1 will give us 2. Is that not so? Minus b is 3, then 2 times 3 is 6. So 2 minus 6 will give us minus 4. That minus 4 crosses to the right hand side, become plus 4. Minus 3 plus 4 will give us what? 1. Therefore, d is equal to 1. Our problem is solved. We can now say that our yp is equal to, we've obtained all the constants we introduced to yp. A is 1, fixing 1 there. 1 times x squared will give us x squared. And then b is what? Let's say b is 3. Fix it there, becomes 3x. And then d is what? 1 plus 1. The general solution for this problem thus becomes, the general solution becomes, look at it. So it will be y equal to yc plus yp. Or yc is what? Yc, look at it, that is c1 x plus c2 in bracket exponential x. Then plus, we're now going to add yp, and yp is this term, which is, let's start with the lowest degree, 1 plus 3x, and then plus x squared. And this is how simple we've actually gotten the result, general solution of this differential equation. We shall take a short break. When we're back, we solve the question number 4 using the IVP given. Let us now determine the IVP of the differential equation in question 3. You would recall that before the break, we obtained these to be the general solution of this differential equation, with this being the complementary function and this the particular integral solution, alright? So we have this as our general solution. From the problem given to us, the IVP, we have, okay, this is question number 4. So number 4 solution. We're given that y of 0, that's IVP condition given, y is equal to minus 2 when x is equal to 0, okay? X is 0, y is minus 2. We also know that y prime is equal to 1 when x is equal to 0. Look at this. So what are we going to do? We're going to substitute directly for this using the first condition. So we'll write for x equal to 0 and then y equal to minus 2, it implies that I'll come over here and put minus 2. So I have minus 2, come here, fix in 0 for x. Of course, you know that C1 will disappear, is that not so? We'll be left with C2, fix in 0 for exponential here. They have exponential, 0 will give you 1. 1 times C2 will give us C2. So this is going to be minus 2 for y equal to C2 for this, then plus, going to have 1, fixing 0 here, fixing 0 here, it goes off. You will see that C2 is equal to, this one will cross to give us minus 2 minus 1, which is minus 3. So we have obtained the value of C2. We shall now proceed to differentiate this general solution so as to be able to apply this second condition. So I'm going to write for x equal to 0 and then y prime equal to 1, we shall differentiate this term. So let us differentiate and see. Differentiate, let me put it down. Differentiate the general solution. The general solution. Okay, so differentiate the general solution. Now if you differentiate this y, you're going to get y prime. To differentiate this term, we want to take note that this is a bracket times this exponential. So you multiply the bracket with the exponential, you're going to use product rule of differentiation. We shall keep the bracket constant and differentiate exponential x. If you differentiate exponential x, you still get exponential x. Is that okay? Times the bracket you kept constant, so that's going to give us c1x plus c2, and then exponential x. Please take note. Suppose this x here is bearing any number or whatever, you do your major minor derivative there by differentiating the major function and then differentiating the minor function. Is that okay? Alright, this time around is going to be plus. Take note that we kept this bracket constant and differentiated this exponential. So this time around I'm going to keep the exponential constant and then differentiate the bracket. If I differentiate the bracket, what will I get? Differentiate c1 with respect to x. It's going to give us c1. Is that okay? Because the derivative of this x that will give us 1. 1 times c1 will give us c1. Come over here and differentiate this c2. It's a constant, so you get 0. We are done differentiating this part. We'll come here and then differentiate. The derivative of this one is 0, so it goes off. Differentiate this 3x, and then you get 3. Differentiate x squared, you get 2x. So this is the derivative. We shall now apply the condition. We shall now apply the condition. It implies that y prime, what's the value given to us, is 1, so I will fix in 1 there. And that will be equal to, we move on, c1 times x. And what's the value of x? X is 0. 0 times c1 will give us 0, it goes off. Fix in 0 here, you have exponential 0, which is 1 times c2, that's going to give us c2. Come over here, you have plus, exponential 0 is 1. 1 times the value of c1 will give us c1. Then plus 3, this is 2 times 0, giving us 0, it goes off. Already we know the value of C2. C2 is minus 3. Alright, so fix minus 3 here for C2. It's going to be minus 3 at this point, plus this 3. And minus 3 plus 3 is 0. Therefore, we've obtained our C1 to be equal to 1. Good. At this point, we can smile. We've gotten the constants of integration. We can now substitute into the general solution. So it implies that going to the general solution, we're going to get y to be equal to, you're going to substitute for c1 and c2. c1 is 1, so it's going to be 1 times x, giving us what? X. Alright, then plus, what is our c2? We obtained our c2 here to be minus 3. So this plus will change to minus. Is that okay? So let me change it. It's going to be x minus 3, because c2 is minus 3. And close this in brackets, exponential x. And then plus 1 plus 3x plus x squared. And of course, this becomes the particular solution to this problem, our answer, right? So we've obtained the IVP solution, which happens to be the particular solution to this DE as given with these initial value problems.